Yes, a very good morning, children. Today's class is about iteration and recursion, which is one of your logic technique, algorithm techniques. Is it clear? Yes. A little variation between your iteration. You check the condition till it is true. You keep on repeating. That is called as iteration. You repeat. You divide your function into subfunctions and you keep on executing. And the solution of the sub problem combined together will be the solution for the original problem using a base condition that you call it as recursion. Okay. Yes. The topics as usual, iteration, recursion, invariant, loop invariant. Many examples are there. A few examples I'll explain in this class, and the remaining the thing will be continued on Thursday's class. Okay. Yes. What is iteration? Iteration will repeat a set of statements again and again till the condition is true. Okay. And if it is false, it stops your repetition. So what are the two steps involved in your iteration? Evaluating the condition. Evaluating means testing the condition. If it is true, you execute the statement. So these are the two steps. Test the condition, execute the statement if it is true. Test the condition, execute the statement if it is true. The condition is false, you stop your execution. Okay. Next one is your recursion. Closely related to iteration, using recursion, we solve a problem with a given input. By solving the same problem with a part of the input, that is a sub-problem, and constructing a solution to the original problem, you call it as your recursion. Yeah? Yes. Next one, you call it as invariant. The terms may be vague and new children. As it's being explained, you understand as it is. Is it clear? So invariant. You are having an expression, clear? If the S is equal to A plus B. Clear? Whatever may be the value of the expression or whatever it is, if the expression is going to remain unchanged, that is add and give the value to S. If that work is going to remain the same, means that expression is called as an invariant of the assignment. Okay. Example, if I say S is equal to A plus B. Next time, if I'm going to say S is equal to give some other value, it's going to remain the same work as addition means, then it's going to be an invariant. Better example, I'll show it in the remaining slide. Next term, you have loop invariant. The body of the loop is said to be loop invariant when it satisfies these four conditions. Start of the loop it should be true. Start of each iteration should be true. At the end of each iteration it is true. At the end of the loop. What is loop and what is iteration? Just say in the next slide. So this before checking the condition, that is called as the start of the loop. Entering into the condition, if the condition is true, you start executing a statement that is called as your start of the iteration. After executing the statement inside the loop and you want to go back again, after execution means end of iteration, and go back again, check the condition. True means continue. Yeah, like this you continue. If it is false means you come out of the loop. That you call it as end of the loop. The start of the loop, end of the loop. Start of your iteration and end of starting your execution of your statement. You call it as start of your iteration. Completing the execution of your statement inside the loop, you call it as end of iteration. When the condition is false, you're coming out of the loop means you call it as end of the loop. In all these four cases, if my body of the loop behaves the same way means, then you call it as loop invariant. Okay. Yes. The next we go with an example. Invariant. First is an example for your invariant a to the power of n. I want to calculate a to the power of n. Generally 2 cube, how you'll write 2 into 2 into 2. 2 into 2 into 2. A is 2 and n is 3 means 2 cube means you say 2 into 2 into 2. So clear. So in that case, what you do is first you'll multiply 2 into 2. Clear? Next you'll multiply 4 into 2 8. Okay, so that's the concept you usually. You start your product by 1 and you start your power by 0. And my A is my number. My output should be P is equal to A to the power of n. You understand that n is missing here? P is equal to A to the power of n. Okay, and what is the action I'm going to do? P comma I. is equal to P is equal to P asterisk A and I is equal to I plus 1. Whatever may be the value of my I, whatever may be the value of my A, I am going to multiply it by B and I am going to increase my value by I. That's why you call it as P is equal to A to the power of I as your loop invariant. Anyhow, I get my answer as what? P is dependent on the value of I. Whatever may be the value of my formula is A to the power of I. So that's called as loop invariant. Now coming back to the explanation in this table, you have each row here. You have each row is called as an iteration. This is my start of the loop and this is my end of the loop. You're going to calculate, example, you're going to calculate 2 to the power of 5. We're going to calculate 2 to the power of 5. Clear. So in this case, we start with P is equal to A to the power of 5. That is 2 to the power of 0. I is 0. We calculate 2 to the power of 0. This is my start of my loop. 2 to the power of 5 is my end of the loop. 2 to the power of 1, 2 are called as my iteration start and end. Can you understand? Respectively, it starts and ends in the same loop. Each row is called as your iteration. So when the loop ends, my P is equal to AI is still true. Still my answer, I'm getting the product answer, but my value of I is equal to 5. Therefore, P is equal to A to the power of 5. So in general, the loop ends with P is equal to A to the power of n. So P is equal to A to the power of n is called as your invariant. Can you understand? So satisfies the specification. Therefore, it is a loop invariant. P is equal to 8 to the power of n is called as a loop invariant. See the next one, you have a chocolate problem. See, first of all, you take your dairy milk or Cadbury's chocolate. You know very well it is divided into small squares. Okay. Now we'll be using three variables. One is for the number of squares is your n. Okay, number of squares we use it as your n. The number of peas in your hand. Before cutting that one single piece in your hand, that p is equal to 1. You have not cut so far. So my cut is equal to 0. Can you understand? And you keep on repeating. Earlier for last exercise, we didn't bother about how many times you are going to cut and how many pieces you are going to. We just said we are going to cut the pieces P and C is cut. But here for an invariant condition, we are going to repeat the process till my number of squares and the number of pieces are equal. Till my number of squares and the number of pieces are equal. Can you understand? In that case, see how it's being explained over here. Okay. So P comma C, I'm going to start as P start value of my piece is 1. For my cut it is equal to 0. And I'm going to repeat this increasing, cutting, piece increase. Cut increases. When you cut, the cut is increased by 1. When you and but my piece is increased by 1. For one cut, my C is increased by 1 and P is increased by 1. Any of the increasing process is same for both P and C, only the start value varies. Okay? Yes. Now therefore, when I subtract P minus C, that will be equal to A. P minus C will be is an invariant of the assignment. If I substitute P plus 1, if I substitute C plus 1, I'll get back P minus C. P plus 1 minus C minus 1. So I'll get back plus 1 and minus 1 will get cancelled. I'll get back P minus C. So whatever may be the value of my P, whatever may be the value of C, final expression is going to be P minus C. So P minus C is called as an invariant to this assignment P plus 1 and C plus 1. Can you understand? Yes. I'll explain it a better way through the boards and then afterwards. Now coming back to the final conclusion, my P minus C will be equal to 1 is called as the loop invariant. Okay? And you say final, how many times you repeat the loop till my P is equal to n. The P stands for the number of pieces and n stands for the number of squares in that pieces. Okay? And substitute this P in the n in this P. Okay? N, your substance P is equal to n. You say n, P is equal to n means n minus C is equal to 1. When you reverse this, you go with your expression, you bring your n this side. Yeah. What will be my n? N is equal, sorry, what will be my C? C will be equal to n minus 1. Bring the C this side and 1 this side. So what will be the minus C when it comes to C become plus C. And 1 comes over here, it will become minus 1. So my C will be equal to n minus 1. So finally, what is the conclusion? Since we started with a cut with 0, my number of cut will be 1 less than the number of squares or the number of pieces. Isn't it? Because we started piece with 1 and cut with 0. Initially itself, we know my number of cut is less than my number of piece by 1. Okay. So finally also, my number of cut, clear, is less than 1 less than the number of piece. Can you understand? So that is the relationship that is called as your invariant, and the flow chart is over here. Okay. So the next one is your recursion. See the recursion example, we may have many ways to think, but as an explanation for our recursion, the problem is explained like this way in your textbook. For example, there are 4 to 5 students standing in a queue. The teacher doesn't know how many students are standing in the queue. She wants to find out how many are there in the queue. She's not going to stand up and count how many students are there. Neither each student is going to count back and say how many students are there. Not one student is not going to give the answer. Clearly understand this. The teacher is in front. So 5 students are standing in front of the student. The teacher is not going to get up and count personally. That's one. And if the teacher is going to put a question to the first student is not going to go back and get the count and get the solution. So problem is being transferred, the question is being passed on to each student, and the answer from each student is combined together to give one solution to this student. Can you understand? Yes, I'll explain this. See, the first two. Assume there are 4 to 5 students there. Clear? What will happen over here? The teacher will ask the first student A, how many students are at the back? So A will ask the question is raised now. There are no solution. The question is raised now to B. A will ask B, how many students are there? B will ask C, how many students are there at the back? C will ask D, how many students are at the back? D will ask E, how many students at the back? So at the last, E doesn't have any person at the back to ask the question. Now E starts giving the solution, or E starts giving the answer. So E will say nobody is there at the back. So D will conclude. D will say to C that one student is at the back. C will say to B that two students is at the back. B will say to A that there are 3 students at the back. A will say to the teacher that there are 4 students at the back. So the teacher will come to a conclusion that including A, that there are 5 students standing in the queue. This is the meaning of recursion. Is it clear? Yes. Next. Now the same thing, we consider a function called as length with 5 students, and this is my input value 5. This is my input value 5. You subdivide your function like this. 1 per student, 1 plus length of BCDE. What is the length of my BCDE? 2 plus B is over. So 2 plus length of CDE. 3 plus length of DE. 4 plus length of E. And then 4 plus length of E is what? Only one student. So 4 plus 1 is equal to 5. So finally, my length of A, B, C, D is equal to 5. You are dividing your problem into sub-problems, and then finally the last person is giving solution, and the next person and the next person, finally you get the answer. Can you understand this? Yes. What are the things kept to be in mind when you're talking about recursion? There should be at least one base class. That means the final person, each should have an answer saying that there is nobody at the back of him. If he is not going to reply anything, means the entire solution will not be dead. So my E is going to be the B's case, where he is going to say that nobody is there, only I am there. Okay? So D will come to a conclusion from that solution, and then C and then D. So that you call it as a base case. Now initially we have the teacher has baked up the problem, not the teacher has put a question to A has put a question to B, that is you are breaking the problem into sub-problems. Okay? Expecting that the person will give the reply. Okay? Assuming the solution for the sub-problems are given by the recursive concept. And another one, the size of the input. The size of the input to the subproblem must be strictly smaller than the size of the given input. The size of the input is 5. The size of the length of sub problem, this is 4, this is 3, this is 2, and this is 1. The size of the input sub problem should be less than the given input. Okay, these are the three important points to be kept about your recursion. And finally, there's an example. The same problem we explained with a to the power of 5. Here we are going to explain with your power function using recursive method. So first you start with power of 2 comma 5, which is equal to power of 2 comma 4, 1 less. 2 into 2, power of 2 comma 3. Like that you go. Power of 2 to the power of 0, where you know that when 2 to the power of 0, any number raised to the power of 0 is 1. This n is equal to 0 means my answer is 1, my recursion stops. When my answer is 1, my recursion stops. Okay, so this is called as your base case. Till if my n is equal to 0 means my answer is 1. So this is my base case. Okay, otherwise you keep on repeating your function till my base case is satisfied. This is called as recursion, and this is an example for your power using recursive function. Thank you, children. This week only we have the video and the PPT to be given to you. I will continue the rest of the explanation and the notes in the next class. Thank you, children.